This is our group's lab final over Archimedes Principle presented by Isaac Hanson, Austin Rotinsulu, and Kristen Sihotang. The objective of this lab is to test and confirm Archimedes' principle, which is stated by the equation below. We will be confirming that buoyant force is dependent on liquid density and volume displaced, and not dependent on object density. We tested this by submerging cubes of the same volume but different densities into liquid also with different densities. In the equation stated by Archimedes' principle, which is F sub b is equal to negative rho multiplied by v multiplied by g, where F sub b is a buoyant force in newtons, rho is the density of liquid in kilograms over meters cubed, v is the volume displaced by the object in meters cubed, and g is the acceleration due to gravity, which is 9.766 meters per second squared in the lab. The right side of the equation is negative because buoyant force is opposite direction of g, which is the acceleration due to gravity. The equation on the bottom is explaining the units of each of our variables and how they cancel out. First, newtons are equal to kilogram times meters per second squared. On the right side, density is kilograms per meter cubed, volume is meters cubed, and acceleration of gravity is meters per second squared. The meters cubed of density cancels out with meters cubed of volume. This leaves us with units that work and that we need. During the experiment, we will be using grams per milliliter, and it is important to convert this to kilograms per meters cubed in the end.
Materials for this lab include the Pasco 850 and force sensor, a heat pad, this is optional, 2 metal rods, one that can fit the bench, and a clamp to attach them, a graduated cylinder, assorted masses, a scale, a caliper, 5 cubes of assorted materials, salt or sugar can be used for this lab, string, scissors, and finally, a laptop with Pasco capstone. To begin the experiment, set up the apparatus as shown in the video. The force sensor will need to be calibrated using 2 different weights. We use 25 grams and 50 grams. Next, measure the mass and side lengths of each cube. Calculate the volumes and find the density of each cube by dividing its measured mass and calculated volume. Next, tie each cube with a string of equal length. After that, weigh the large graduated cylinder and record its mass. Add 100 milliliters of water to the graduated cylinder and record its mass again. Next, hang each cube by their string from the force sensor and record each initial force reading.
The next step is to fully submerge each cube into the liquid of the graduated cylinder. Be careful to not hit the walls of the graduated cylinder as it will make the reading less accurate. Record the force reading given by Pasco capstone for each material. After recording each reading, place the graduated cylinder onto the triple beam balance. Some mass may have been lost during the transfer of the cubes, but that is okay. Simply calibrate the triple beam balance to be 20 grams more than the previous reading. Add sugar until the masses are balanced. Mix thoroughly until the sugar is dissolved. If the sugar is slow to dissolve, a heat pad may be used to speed up the process. Record the new volume and mass of the liquid. Repeat steps 7 and 8 until 5 fluid densities have been recorded. Some calculations are needed for the results and conclusions. Calculate the densities of the liquid using the mass and volume readings. Calculate the cube densities using each individual mass and volumes calculated from the side lengths. Calculate the buoyant force by subtracting this experimental reading from the initial free-hanging force. Discard values where cubes floated or where buoyancy force is greater than the weight of the cube. Here are our results for the buoyant force. Again, buoyant force was found by subtracting the measured force by the initial force taken when the mass was not submerged in anything. The average buoyant force of each density was calculated as well to be used for graphical analysis. The side length of each cube was used to determine its volume. Using this volume and the recorded mass, the density of each cube can be calculated using rho equals m over v. Here, we compare the density of each object with the buoyant force applied to it when submerged in liquids of different density. Graphing this data, we can see that there is no correlation between the density of the object and the buoyant force applied by the liquid. Low-density objects have very similar buoyant forces as high-density objects. This supports that the buoyant force is only dependent on the density of the liquid and the volume displaced.
Here are the liquid densities calculated. The mass and volumes were recorded after adding sugar but before each trial. The density increases by about 0.06 grams per milliliter for each trial. Comparing the liquid densities by the average buoyant force of each trial, we can analyze this relationship. As you can see by the graph, buoyant force is directly related to the liquid density. The equation of the trend line is y equals 0.169x minus 0.0243 with an r squared value of 0.9748.
After looking through the data, we concluded that there is a linear relationship between buoyant force and the density of the fluid, and there was no relationship between the buoyant force and the density of the object. The slope of the graph is the buoyant force over the density of the fluid. Using the previously stated equation for buoyant force, we also know that the slope is equal to the volume displaced times gravity. Therefore, dividing the slope by gravity will give the volume in
Meters cubed,
which can be
divided
by 1,000 to find the volume in cubic centimeters. To compare this calculated data with our measured data, we will be comparing the calculated average side length with the measured side length. To do this, we will need to take the cube root of our previously calculated volume in centimeters cubed, thus giving us the side length in centimeters. The calculated side length was 2.58 centimeters, and the average side length of the cubes was 2.49 centimeters, thus giving us a percent error of 3.6%. This same method could be used to accurately find the volume of an object that's volume is not easily measurable.